Here's a tutorial on the Physics Chapter 3 Fakie. I'm not going to be slowing down that much. You can always hit pause. You can hit rewind. You can ask me for questions later. The plane's initial velocity when it hits is this. That was a typo. So this is velocity initial. It's got to come to a stop. So the velocity final is 0. We are looking for the average acceleration. That's A. And well, we know the time t here. So if we assemble what we need, we know T, VI, VF, and we need A. And remember, we don't know D, so don't pick a formula with that in it. And here's the formula we're going to need. That's 0, 90, A is unknown, 15 seconds. Subtract this over and divide under. The seconds, this seconds will stay on the bottom. It will not cancel anything out. And you'll get 90 divided by 15. It'll stay negative. Remember, this turned negative. And you'll get meters per second squared, which is the true units for acceleration, and it should be negative because it's slowing down. It needs to be negative. That's not a mistake. At this point, we know we need D. We know AVF, VI, T. There's a lot of stuff that could work up here. I chose this one just because it doesn't have squares in it and stuff like that. Remember, VF is 0, so this adds up. Times, and we've got D. This second is going to cancel out that one and give you meters. We know before Bill starts accelerating, this is his initial velocity. And then he accelerates at this speed. He goes through a distance, and we're looking for final speed, final velocity. So we have a units problem because this is in kilometers per second squared, and this is in meters, and that's in kilometers per hour. So I'm going to take my acceleration and convert it. You could convert a number of different things. You just need to get them all in the same units. I thought it would be easier if we did kilometers per hour. I added this actually, didn't I, in kilometers per hour. So what I'm going to say is I know that there are So to get this into kilometers per hour squared, I can't get the squared out, so I'm going to have to leave that for a moment. I'm going to need the number of seconds per hour squared. So it's the squared number, or it's going to be seconds squared per hour squared, and that is the fact that there are 3,600 seconds per hour. So the number of seconds squared per hour squared is the square of this number, which is that. And when I then multiply by this, the seconds squareds cancel out. It gives me per hours squared. And that looks a bit weird, but when it was per second squared back here, no one argued, right? So this is still per time squared. We're going to deal with the units in a bit. It will work out. I wanted this into kilometers because that's in kilometers. So I'll convert this using 1,000 meters per kilometer. The meters cancel out, gives me kilometers. Now I can put this onto here. And as I recall, this is the one where I probably made like 3 mistakes, but the initial velocity is 7. Here's my kilometers per hour squared. This is my A value. Don't forget the 2 here. And here is my kilometers traveled while accelerating. So it's going to be this times this times this. And then don't forget to square that. At that point, we have the units of kilometers squared per hour squared. And here we also have kilometers squared over hours squared. And then we can add them up. Remember that it's equal to VF squared. So when we add them up, the units are kilometers squared per hour squared here when we add them up. And then to find VF alone, we need to square root both sides. And that's why the units do end up working, because our final velocity is in distance per time, which is a speed, a velocity. So that is right, and it does work. On number 3, the person at the top of the building doesn't just drop the ball, she throws it down. So we can't say that VI is 0. We'll say that it's here VI, 4 meters per second, and when it's 5 meters from the top. And then we know time to reach the grounds. So the first part is how tall is the building. So you want D, we got to have D in our formula. We know VI, we know T, and we know A because it's gravity, right? And some people will just write this as small g. So if you look up at the top, this is the formula that works, because remember, we have to throw out everything that has VF in it. We don't know that, and we're not asking for it. So we put in the initial velocity times 1/2. If initial velocity times time times plus the 1/2 times the acceleration times the time it accelerated squared. So square this times this times this times this. Notice the squareds, the seconds cancel out. And here the second squareds cancel out. Now we have meters, and meters can add to meters, and we get meters. But remember, the height of the building is 5 meters more than whatever we just found. So this is the height of the building. How fast is the ball moving when it hits the ground? And so now we do need VF in there, but the difference is I don't need D in there. The problem with having VF over here was that I would have D and VF unknown both at the same time. Here I don't need D. Actually, I could get quite a number of formulas. Now that I know D, I could use many different formulas. This seemed to be the simplest to me. Here's VI. Here's the acceleration and the time under acceleration. Multiply. One of these S's cancels out one of those. And now I can add meters per second plus meters per second. And that is, in fact, the correct units for a velocity. So at the start of braking, this is the speed or velocity. So that's VI. The car comes to a halt, so that's got to be VF is 0, right? The time it took to do that is 3 seconds. And we are asking for the distance. How far did the car travel in meters? Now, the difference being that this isn't in meters, so I'm going to have to convert that. And I want it in meters per second also, because that's in seconds. So why don't we just convert this one thing instead of these two things? And but I'm going to have to convert it to meters anyway at some point, right? So let's just convert both of these. There are 1,000 meters per 1 kilometer and 3,600 seconds per 1 hour. And so the hours cancel out and the kilometers cancel out. Well, and you might notice that you can just then cancel this out and call that 3.6. That's what that dot is. If you want to just do it the easy way, you can notice that crossing out this and turning this into 3.6 is the same thing. And then you get a value for VI, because this was VI, right? Now we can put that in. Now what do we have? We have VI, we need D, we know VF because that's got to be 0, and we know T. Notice we don't have A, and we're not asked for A, so you can't pick anything that has A in it. That's why most of those formulas up at the top won't work. So we're going to put in VI, VF is 0, and T, and multiply, 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 and you get D in meters, because this seconds cancels out that seconds there. On 5, we just dropped the bowling ball. So the initial velocity is 0 because you dropped it. We know the height, so that's the distance to the ground. We know the acceleration is going to be from gravity, so that's gravity. And we're looking for the velocity of the ball when it hits the ground, so that's VF. So we need some equation with all those things in it, and this is the one. Remember, we don't have time, so we need to throw out everything with time in it. This is 0, so that's fine. That's squaring that is no problem. This times this times this. And don't forget to square root it at the end, and that's where the squareds on the units go. They disappear when we square root this whole right side. When does the ball hit the ground? Now we need T, but now we have VF. And so the easiest one is back to this one without all the squareds and a bunch of other terms in it. And this is VF. Back from this answer here. VI is still 0, AT, and so just divide this one under and we get T. What we're going to get, though, if you want to watch the units, is we get meters squared over meters per second squared, and tops cancel out and bottoms cancel out, but the bottom of the bottom is the top of the top, and the remaining S comes to the top, and that's why the unit is seconds. On 6, we throw the ball straight upward. I don't know quite how you do that, but let's pretend, or you fire it out of some machine straight upward. So it's going to rise and fall back. And so if you throw the ball with an initial velocity of this, that's your VI. So how long does it take is the time, right? So we know that the acceleration will be downward. Here's gravity's value, and it's going to be negative. If this is a positive value up, then this must be a negative value, must be. Otherwise, gravity pushes the ball off the earth. And we're looking for time. And we know at the top of the arc, the velocity finally at the top will be 0. So we're looking for time to 0. So that means that the velocity at the top is the final velocity for that time, and it's 0 because the ball comes to a stop vertically. So what we have to do is subtract this over, and then we can divide under, and the negatives disappear because you can't have a negative time. And we have the same unit configuration as from 5, fraction over fraction, and the remaining seconds on the bottom come to the top. How far will it rise? So we need distance to the top. We know again, VI is this, VF is that to the top, and now we know time. And this seems like the easiest formula to me. And this adds up and then multiply, and we get D. This second cancels out that one. What's the average velocity during this period? Well, the average velocity will be really easy if you know the overall distance, the overall time, and we do. And then we can just divide under, and the units do not cancel out. Meters per second is the correct units for overall velocity. How long will it remain in the air? So this is really easy once you think about it. The ball has to go up and then come back down, and presumably it will take as long to go up as it comes down. Actually, this should say, oh no, before you catch it at the same distance from the ground. So then we've accounted for that. So if you catch it at the same spot above the ground that you threw it, then the distance isn't cheated. It's not falling farther than it rose up. And so it's just going to be 2 times the time up. The total time will be twice the time to the up to the top. Now, when things fall, the weight is immaterial. We've talked many times about how everything tries to fall at the same speed, ignoring wind resistance, of course. And we're going to say that on some high diving platform, her wind resistance is going to be pretty low, and she's not wearing a parachute or anything. So that is a distractor. That's immaterial. We know that the distance to the water, what's her acceleration? Well, the acceleration is, of anything in free fall, is that, isn't it? The acceleration is always from gravity. So that's not even any math. That's just asking if you understand the point of the acceleration under gravity. So how long does it take? So we're looking for time. And remember, we don't have time. We need time in here, but we don't know it. And we don't have VF. So we can't have both these things, or we'd have 2 unknowns in one equation, which is impossible. We have to have time, but we can't have VF. And so that's why I chose this one. Don't forget to put t squared. I've done that mistake. Distance is 10 meters. The initial velocity, because she just hops off the platform, is 0. And so we can go multiply and then divide under. And don't forget to square root both sides. And that's where the squared term on the second comes off, and we just get seconds. When this divided under, the meters canceled out, and the squared second squared went to the top. What's her velocity as she hits the water? So now we are looking for VF, and we know VF, VI, acceleration is gravity, and we now know distance. Actually, there are a number of formulas that would have worked because we now know time. That was what we figured out, wasn't it? Not distance. We knew the distance. I chose this one. There are many others that could work. Actually, probably almost all of them could work because we have so much information now, but this is the one I chose anyway. VI, because she hops off, is 0. VF is unknown, and A is gravity, and distance was 10 meters. So multiply, and don't divide or anything. That's it for the right side, and then square root both sides, and that's where the squareds go on the unit. On D, she comes to a vertical stop in 7 feet after she hits the water, of course. What's her average acceleration vertically in the water? So when she hits the water, her initial velocity coming to a stop is the velocity we got when she hits the water, right? So we're going to take this as final velocity in the air and take it as initial velocity in the water. Now we know the distance that she traveled was 7 feet, but um, this is in meters. So we're going to go and transfer this to meters. Using, I looked up the meters per feet, and I need to include that, don't I? Okay, so if we know the conversion factor, then we go multiply, and now we have meters. Uh, we don't have t. Yes, we do. Whoops. Yes, we do have time. But you could choose this formula anyway. It's not too bad because we know that when she comes to a stop in the water vertically, because she has to come back up, right? At some point, she must have stopped going down. We know she's going to come back up. So at some point, her vertical speed must have hit 0 so she could turn around. So that's got to be 0. And then she has stopped vertically. And her initial velocity was 14 meters per second vertically. And we know that the distance was this now, and we're looking for A. A is not gravity, remember, because she's slowing down uh, because of the water. We're looking for A. So what we're going to do, because this is plus here, we're going to square this and subtract it over here so it gets negative. And then we're going to say 2 times this and divide. And the meters here is going to cancel out one of those, which does leave meters per second squared, but that's the true type of unit for acceleration. You should have distance per time squared.